Hello, my name is Noah Stansel, and today we're going to be demonstrating a little bit of fluid dynamics here by calculating the Reynolds number of both cold and hot water flow in your kitchen sink, or dormitory sink, because that's all I have. So we're going to assume that the cold water flow is going to be approximately 10 degrees Celsius, while the hot is approximately 65 degrees Celsius. So to find the Reynolds number, you're going to need to find the density, velocity, diameter of the faucet, and the viscosity of the water. The density, velocity, and viscosity are all dependent on temperature. So to find the hot flow, we're going to have to solve for all three of those all over again. So we will begin by finding the diameter here. And it might be kind of difficult to tell from here, but it is approximately 15/16 of an inch. So record that here. And to translate 15/16 of an inch over to meters, which is what we need to solve the equation, we're going to be multiplying all of this by 0.0254. 15/16 times 0.0254 meters gives you 0.0238. 0.0238 meters. All right, we're going to find the area, which we will be using later, by plugging in the diameter to this equation, which is the area of a circle. So pi is times d over 2 squared. So pi times 0.0238 over 2 squared. Okay, so pi times 0.0238 over 2 squared equal to 0.000445. Okay. Meters squared. And to find the density of the cold water flow, we're going to use a handy dandy website called the Engineering Toolbox, which has been very helpful in my engineering career so far. So you can see I already have 10 degrees Celsius inputted there, and we are finding the density, calculate water density, and we need it in kilograms per meter cubed. So that's going to be 999.6. Just going to plug that in over here. 999.6 kilograms per meter cubed. And then we're also going to go ahead and find the viscosity while we have the computer pulled up. The viscosity of water at 10 degrees Celsius is going to be found in newtons seconds per meter squared, which is going to be 0.00130076. And then record that as well. 0.00130076 newton seconds per meter. And then we need to find the time it takes to fill a 1 liter container of water with 10 degrees Celsius. So our container that we're going to use for your liter is going to be this little Tupperware here. And you see that it's marked at 945 milliliters. 1 liter is actually 1,000 milliliters. So we're just going to estimate it's going to be just above, about where the tip of my thumb is. So we're going to fill up there and we're going to time it using that there. All right, let's go ahead and flip this bad boy on. All right, start the timer. We're going to watch. So just add that second piece there, might be kind of difficult to see. All right, and stop. Timer is at 10 seconds and 0.18 there. Record that, so 10.18 seconds. And we're going to use that time to find the flow rate of the fluid, so 10.18. And to translate it into meters cubed per second, which is what we're going to need for the rest of the equation, we're going to have to simply divide it by 1,000. Just going to plug it in here. So 1 divided by 10.18 times 1,000, which is equivalent there, be 0.000098. 0.000098. Okay. And that is meters cubed per second. And then now that we have the flow rates in the area, we're going to use the two of those to find the velocity of the cold water. So 0.000098 all over 0.000445. See what we get there. You get 0.2207. We can round that to 0.221. 221 meters per second. And now we have solved for everything we need for the Reynolds number. So we're going to collect all the data for the cold here, and we're going to flip pages and plug it into this equation that I already have handily set up. Ignore that. It's going to be 999.6, and then the velocity we got was 0.221. The diameter was 0.0238, and then the viscosity was 0.00130076, 0.00130076. All right, so 999.6 times 0.221 times 0.0238, all divided by 0.00130076, get about 4,021. Okay, and little bonus here, that is higher than 2100, which means this cold water flow is turbulent. All right. Answer for the cold water flow there. Now we need to go solve for the hot. So we already have the diameter and area for this, so we can go ahead and skip that step. Let's go and use engineering toolbox to find the density of the water at 65 degrees Celsius. The water density at 65 degrees Celsius is going to be 980.53. 980.53 kilograms per meter cubed. And then the viscosity of 65 degrees Celsius, the dynamic viscosity to be specific, is 0.000432. 0.000432 Newton seconds per meter squared. All right. So now we need to find the time it takes to fill up the container there. Empty out our water and turn it on until it gets hot. Might take a second. Almost there, warming up. Okay, getting pretty toasty there now. Now we're going to insert the container there and start the timer right up with the wide array. All right. Let's see, let's watch there, second line. All right, timer has stopped. It is at 11.5 seconds. All right. Plug that in over here to find the flow rate. Divide it by 1,000. It's going to be 0.000869. We're going to round it to 0.87. 0.000087 meters cubed per second. And for velocity, I'm going to plug in the flow rate and then the area, which is the same for both cold and hot. Let's see. 0.000087 divided by 0.00445. Oh, there's another zero there. Okay, so you get 0.196. 0.196 meters per second. All right, collect all those. We go back to where the Reynolds number is. All right, so the Hot water density is 980.53. The velocity, 0.196. The diameter, 0.0238. And then the viscosity, 0.000432. Sorry if you can't read that. Okay, 980.53 times 0.196 times 0.0238 divided by 0.000445. Oh no, that's 432. My apologies. So we're gonna get 10,588 approximately. That is the Reynolds number for the hot water. And that again is much higher than 21,000 or 2,100. So that means this water flow is also turbulent. All right, good job. We found the Reynolds number of both a cold and hot water flow in a sink. And thank you. Thanks for listening.